I'm supposed to record this anyway. Well, so vector fields, what are they? Yes, let's look at one example. So let's look at a very, very simple example of vectors, and we're going to also graph some of them. And let's see. So, all right. So we have the vector field given by big F of x, y. Again, these are no longer going to be some r of t or r of s for the arc length function. So it's given by x of I, which, by the way, for notation, this is the same as saying big F of x, y, or rather, without the big F, that's xi plus 0j, which is the same in component form as x comma 0, which is what I express here in our table. All right. So we're going to plot some vectors related to give to some given points. So in this case, what are we going to get? Well, so I'm going to plot some points. I have the point 1 comma 0, 1 comma 1, negative 1, 1, negative 1, negative 2, 3, 0, 3, 1. So just some random points. So what are we going to do? We are going to plug in these values of x and y into our x's and y's into our vector field. Well, this one is a very simple case in which all the y components are going to be 0. So that's a given. That's a freebie. That's great. Well, so the x component of the vector will be, in this case, just x, which is the same x coordinate of the given point. So that's a 1, 1, negative 1, negative 1, 3, and 3. So what are we going to do? Number one, we're going to go to the point 1 comma 0, which is this point. This is going to be our initial point for the corresponding vector, which is 1 comma 0. All right, that's one vector. Maybe I should use a different color for contrast. So that's the vector, right? Now at the point 1 comma 1, what do we have? So if we go up to the point 1 comma 1, that's going to be the starting point, the initial point of the vector, and that's also 1 comma 0. What about point, on the negative side? So that's a negative 1 comma 1. So that's our initial point. In this case, we're going to go for the vector negative 1 in the x direction and 0 on the y direction. And for the point negative 1 comma 2, it's basically the same vector, right? And what about, okay, let's look at other more interesting points. The point 3 comma 0. Which one? The number 4, negative 1 comma 0?
Is it negative 1, negative 2?
Yeah, so negative 1. Oh, negative 2. That's true. So negative 1, negative 2. Well, it's going to be the same vector, but yeah, thank you. So that's the vector associated to that or paired to that point. Now for the point 3 comma 0. So that's going to be the initial point of the vector corresponding to the corresponding vector that is 3 units in length. All right. And for the point 3 comma 1, that's 3 units here as well. All right. Of course, we cannot plot infinitely many vectors here, but I mean, hopefully we can see the pattern. We have more vectors like this, and more vectors here of the same length. So if we were to describe the physical setting of this, because this vector field describes the velocity of a fluid. Maybe we have this some kind of some rooftop here, and well, further some object goes down, see the magnitude of the vector, the magnitude of this velocity, so the further it goes down, it goes faster due to gravity, right? So maybe that's one way to describe what's going on. Or maybe another way to describe, where's my pen? Oh, here it is. Another way to describe this, maybe this is a magnet right here. Maybe this is the pole of the magnet that repels all the repulsive magnets that are pointing to with the opposite charge. I mean, with the same charge, right? Maybe that's another way. So what's the pattern here? Just to briefly describe it in words. Vectors parallel to the x-axis and away from the y-axis, or repelled from the y-axis. So depending on the application, if it's like the fluid or a magnetic field, you know. So let's look at another example. How about that? In the meantime, let me all right. Example number 2, let's sketch some vectors in the vector field given by f of x, y equals to negative y plus negative y in the direction of y and x in the direction of j. Alright? So this is actually, this one has a special name. This one is called a rotational vector field. Alright, you'll see why when you look at the shape that this is going to give rise to. And again, I'm going to plot some vector at some random points, and I'm going to choose the point 1, 0, 0, 1, 2, 0, 0, 2, negative 2, 0, 0, negative 2. Alright, be careful when finding the corresponding vectors, because even though, well, we have, so for the ordered pairs we have them in order, x and y. However, the vector field doesn't have to be in order, because those components, y, I, and j, can contain any random function of x and y. So we're going to find the opposite of the y component, but well, in this case is 0, and x, which is 1. For the other point, the opposite of the y component, which is negative 1. Are you guys following me here? Right? And comma x, which in this case is 0. And then the third vector will be the opposite of the y component, well, which in this case is 0 and 2. And then the opposite of the y component, that's a negative 2. And 0, that's the x component. And the opposite of the y component, that's also a 0, and a negative 2, which is the x component. And last but not least, careful, the opposite of the y component, the opposite of negative 2, isn't that a 2? And x, which is 0. So let's plot some points. So let's go to the point 1, 0. For the point 1, 0, that's this point. I'm going to draw the vector 0, 1. So that is 0 in the x direction, 1 in the vertical direction. Right? See how it changes this time? What's the next vector? For the point 0, 1, which is this point, that's the initial point for the vector negative 1, 0. Okay, negative 1, 0. And then the next vector at the point 2, 0, that's going to be the vector 0 in the x direction and 2 units up. For the point 0, 2, that's the vector negative 2 units. in the x direction and 0 units in the y direction. And two more vectors, so at the point -2, 0, that's going to be the vector 0, -2. It's a vector pointing down. And last but not least, 0, -2, that's going to be the vector 2, 0. Do you see the shape of or the trend for these vectors? It's a rotational vector. It's rotating. Let's see it in Desmos for more vectors, all right? I mean, not in Desmos, on GeoGebra. Let's do another example. Sketch some vectors in the vector field given by f of x, y equals to 3x plus 3y. And this is going to call, this one has a special name as well. This one is called radial vector field. Yes. Oh. Well, the good thing it's still recording here, so. All right, so some random points. Again, I guess the same points. One, 0, 1, 1, 0, 1, negative 1, 1, negative 1, 0, negative 1, negative 1. So let's write down the associated vector. So in this case, well, check the form of the vector field. It goes in order x and y. However, all we're going to do is multiply by 3. All right? So that's going to be 3, 0, 3, 3, 0, 3, negative 3 and 3, and negative 3 and 0, and finally negative 3, negative 3. You guys following me here? All right? Just plugging in the correct order. The previous one was the tricky one because the variables were reversed. And one of them, on top of that, had an opposite sign. This one, well, let's go to the point. Let's go to the point 1, 0. So for the point 1, 0, we're going to draw the vector 3 and 0. For the point 1, 1. We're going to draw the vector that is 3 units in the horizontal direction and 3 units in the vertical direction. For the point 0, 1, we're going to draw the vector 0, 3, that is 0 units in the x direction, 3 units in the y direction. For the point, what's next? Negative 1, 1. That's going to be negative 3 units in the x direction, 1 and 3 units in the y direction. What's next? Negative 1, 0. That's going to be negative 3 units in the x direction, no units in the y direction. And one more, negative 1, negative 1. All right. So I guess you see the pattern, what's going on, right? So in this case, it's like a source of energy, if you will, or a source of some magnetic field, or maybe maybe the origin in this case, it's repelling these forces, but in this case in circular motion, in all directions, not parallel to the x-axis like the first example. In this case, in all directions. We're already familiar actually with vector field, but actually we didn't talk about it because, well, back then we were only studying partial derivatives, and well, our first task in partial derivatives is to find the partial derivative with respect to x and with respect to y. And well, just to review a little bit of it, well, the partial derivative with respect to x was the rate of change in the x direction, while the partial derivative with respect to y was the partial derivative was the rate of change in the y direction. And together in the gradient, that's like a database of or both rates of change, well, or the rate of change with respect to z if we have the gradient in 3D. But also one of the important things about the gradient is that tells us the direction of steepest ascent or steepest descent, right? That is, when we're climbing up the hill at a given point, what's the direction that will be the steepest direction, right? But well, back then we didn't think of of that gradient as a vector field, only as an expression or as a vector that tells us the direction of steepest descent. Okay. So let's review. Let's consider the function f of x y equals x squared y plus 4x minus 8y. So let's find the gradient. So number one, the gradient nabla f f of x y rather, and that's the derivative of f with respect x and the derivative of f with respect y, and that equals to, well, the partial derivative of x squared y with respect x, that's 2xy, and the derivative of 4x, that's plus 4. And with the derivative with respect y, that's going to be the derivative of y, which is 1 times x squared, and that's just x squared plus or minus 8. So that's the gradient, right? Just taking a couple of partial derivatives, and well, so what's this gradient here? So the thing is that, so we're going to have a function f that it's differentiable whether in R2 or R3 depending on where we're working, that is the 2D plane or the 3D space. So the vector field f, which is the gradient, which is a gradient field, and f is actually a potential function for f. That is the function whose derivative is f, and in this case is it's the gradient field. Now, different textbooks are going to use different letters. So instead of talking about little f, which is the original function, that's the letter we use to take the partial derivatives to come up with the gradient. However, this time we're going to work with the gradient, and well, actually later in the chapter we're going to retrieve back the original potential function, and in this case they use the phi, the Greek letter phi, to refer to that function. So let's find the gradient field for the potential function phi of x. So I mean, it's the same thing, find 3 partial derivatives, but instead of taking the partial derivative of f, you're taking the partial derivative of phi. That's all it is. So f with an arrow here, that means that the gradient field, which is nabla of f, so that is the partial derivative of phi with respect x, comma, the partial derivative of phi with respect y, and the partial derivative of phi with respect z. So, well, this is the derivative of a logarithmic function. Yes, it has a lot of terms, but again, to differentiate a logarithmic function, that's 1 over the argument of the logarithmic function, that's 1 plus x squared plus 3y squared plus 4c squared, and times the derivative of this quantity, but well, first with respect x, and that derivative is going to be 2x, comma, 1 over 1 plus x squared plus 3y squared plus 4z squared times the derivative of 3y squared with respect to y, that's a 6y, and for the z component, same denominator, 1 plus x squared plus 3y squared plus 4z squared, and then times the derivative of 4z squared, which is 8z. All right. I mean, it's the same. We're just changing the symbol, f for a phi. All right. So the next couple of exercises are more like to review some of the properties of the gradient. That is that the gradient is orthogonal to the level curves of the function that is represented. So let's see. Let's talk about it. So example number 6, part A. Show that at each point C, and that C is given by this circle of radius 3, the radial vector f described by xy over its magnitude is orthogonal to the line to C at that point. So one thing we might want to recall is, again, from 15.5, the gradient is orthogonal to level curves. All right. So, well, what do we have in this case? Well, so given C, which is x squared plus y squared equals to 9. And you might remember that in order to define the function f of x, we move all terms to the left hand side of the equation. X squared plus y squared minus 9 equals to 0. And this is our f of x y function, for which we will use to find the gradient. And in this case, well, that f equals x squared plus y squared minus 9. So let's find the gradient. Nabla of f, that's the partial derivative with respect to x, which is 2x. The partial derivative with respect of f with respect to y, that's 2y. That's our gradient. And well, so what do we have over here? So when we compare, check this out, when we compare this gradient with a given radial vector field, well, what do we have in common here? We have a common factor of 2. And when we compare with the radial, so that is 2 times r. Well, 2r. What is this r? Well, because this is r right here, which is this numerator, isn't it? The numerator from the radial vector field. When we compare, so f equals the square root of x squared plus y squared. That is the radial vector divided by its magnitude. So what do we have in this case? Well, notice that these quantities, this vector is the same. All we have is different multiple constants. In this case, we have that vector times 2, and in this case, we have that vector times 1 over its magnitude. All right. So that means, what do we have here between the gradient and the vector field? What do we have? We have that they're parallel because those two vectors have the same direction. All they differ by is their multiple constant. So you can have a vector that is, okay, let me do it here. So a vector, okay, this is a 1 unit vector, and this is a 3 unit vector, or 2 unit vector, so to speak. Well, they are parallel vectors. They're going in the same direction. They just have different multiple constants. So what are we going to conclude here? Well, so since nabla f is parallel to f, right? Therefore, f is orthogonal to C. Well, and again, so because f, the radial vector field, it's parallel. That is, it's going in the same direction as the gradient that we came up from C. Well, so if the gradient is orthogonal, also that vector field will be orthogonal, right? Because they're both going in the same direction. For the next idea here on the next page, That's gonna be perfect timing. Now we're gonna show that at each point of C, well, the same C, that is x squared plus y squared equals to 9. This time the rotational vector field, which is given by negative yx, we described this vector field before, but well, this time we're dividing it by its magnitude. This time is parallel to the line tangent to C. Well, so in a way, you can think of parallel and orthogonal as kind of opposites of each other, right? So if it's not orthogonal, then it's parallel, well, unless it's going in different directions. Well, so number one from before, what do we have? F, big F, the radial vector field, and well, this is what we're going to do. We're going to find the dot product between F and the given G. That is the dot product, that is xy over the square root of x squared plus y squared, and dot it with G, which is given by this vector field. That's the rotational vector, negative y comma x over x squared plus y squared. Well, the denominators are just going to be a constant, right? That's not part of the, well, yes, part of the vector, but that's just a constant. Well, so to dot product two vectors, multiply the components. That's x times negative y, that's a negative xy, plus y times x, which is xy. Now, multiplying a radical by itself, the radical disappears and we just end up with the radicand. Well, what's going to happen here? Isn't that going to be 0? Because negative xy plus xy, they cancel each other. That's 0, 0 over x squared plus y squared. That's 0. So what does that mean in this case? In this case, what happens when when the dot product of between two vectors is 0? They're orthogonal. So here we get that F and G are orthogonal. Well, so in this case, since F from the previous part was parallel to the gradient, that's why all all the level curves were orthogonal to that in this case. Since we have them orthogonal, then means that G is parallel to the tangent lines. Now, and you can see it, we can see this in a picture. So if we have, for example, some level curves, maybe just one. Let's look at this circle. And let's look at the set of vectors that are radial. All right, the radial vectors. So the radial vectors, that looks like this. All right. So, can you see the orthogonality between the circle and the vectors that point out of the origin? So that's from the previous part. But what about the rotational vectors? Well, the rotational vectors, in this case, well, are going to be vectors that look like this, you know? Now, these rotational vectors, aren't they really parallel to the tangent lines to the circle?